Okay, this short video deals with finding the least common multiple or least common denominator of two or more expressions or numbers, and some of the reasons that you want to be able to do that. Adding and subtracting fractions is one reason that you need to find least common multiples or least common denominators. Simplifying complex fractions and solving equations, inequalities involving fractions, or what we sometimes call rational expressions. A rational expression is really a fraction where the denominator is a polynomial. Now let's just take a few examples here that are kind of straightforward. If we had to add these fractions together, in order to add fractions or combine fractions or even subtract them, they must have a common denominator. So these two fractions do have a common denominator already of 7. So all we have to do is add the numerators. 2 plus 3 is 5. So we have a total of 5/7. But for these two fractions, 1/3 plus 1/2, the denominators are not the same. This is where we have to find the least common denominator. And that least common denominator is a number that both 3 and 2 will divide into evenly. And that's kind of obvious that 6 is going to be our LCD for this one. So we have to determine what is the multiplier that we need to multiply top and bottom of each fraction by to convert the denominator into a 6. And again, that's pretty easy to see. If I multiply top and bottom of this fraction by 2, I can do that because 2 over 2 is really just the number 1, and any number times 1 is the same number, so I haven't changed the value of the fraction, I've just changed the way it looks. And similarly, to convert this fraction so that it has a denominator equal to 6, I multiply top and bottom, or numerator and denominator, by 3 over 3, or by 3. So this becomes 2/6 for the first fraction. The second fraction becomes 3/6. And now, since the denominators are the same, I can add the numerators, putting them over the common denominator. Okay? Now, when we get to fractions involving rational expressions, this is like a factor, x plus 2. We don't say that x is a factor and 2 is a factor. X and 2 are terms, so the denominator we think of as the quantity x plus 2. So these fractions have the same denominator. That means I can, in this case, subtract the numerators. 5 minus 3 is 2 over x plus 2. For this fourth problem, the denominators are not the same, and I've already put them in parentheses so that we can see that we have to get an LCD. And we're going to see on the next page that we can form the LCD by, in effect, joining together all the factors of each denominator, the union of the factors. So for this fourth problem, the LCD is x minus 1 times x plus 5. This is an expression that both of these denominators will divide into evenly. So I need to multiply top and bottom of the first fraction by whatever expression is required to have me end up with this in the denominator. Well, that will be, this is missing an x plus 5. So I multiply top and bottom of the first fraction by x plus 5. And now the first fraction matches the LCD. And guess what? I have to multiply top and bottom of this one by the missing factor, x minus 1. Now, I'll probably simplify each numerator and then picture combining similar terms. I might do that on scrap paper. Matter of fact, let's do it that way. This numerator becomes 7x plus 35 when I distribute the 7 over the quantity x plus 5. This numerator becomes 3x minus 3. So if you're on a test, this is what you might do on scrap paper. 10x plus 32. So this is going to be 10x plus 32 over x plus 5, the quantity x plus 5, times the quantity x minus 1. Now normally this 10x plus 32, we might factor that before we write it here, because it's possible that after factoring that we'll get a common factor in the numerator and denominator to cancel out. We can see that we can only factor out a 2 here. So this would be 2 times the quantity 5x plus 16. That doesn't match any factor of the denominator, so this is an okay way to leave the problem. But we could also say, well, since nothing is going to cancel out, if I want to, I can multiply these two binomials together using FOIL. X squared plus 4x minus 5. Okay, so we've just rewritten the original problem as one fraction. That's basically what we've done. We've combined those two fractions into one by getting a common denominator. Now let's move on to page 2 and look at some other expressions that we're going to add. We're going to use prime factorization to find the LCM, or least common denominator. And I'm starting with this kind of intimidating problem over here to discuss what we mean by prime factorization and the LCM of these two numbers, 300 and 315, as being the union of their prime factors. Now, how do we find the prime factors of 300? Well, the way I do it is I start by dividing by the least prime number that I can see will divide into the LCD, or the denominator, evenly, which happens to be 2. And since the last digit of the quotient is an even number, I know it'll divide by 2 again. Now I can't divide by 2 anymore, but since these digits add up to 12, 7 plus 5 is 12, I know that this is divisible by 3. Digits don't add up to a multiple of 3, so I move on to the next prime number, which is 5. And when the quotient is a prime number, You're done. So 300 can be rewritten as 2 squared times 3 times 5 squared. Now let's do the same thing for the 315. I'll move down here a little bit further. This number is not divisible by 2, but it is divisible by 3 because the digits add up to 9, which is divisible by 3. 105 is divisible by 3 because the digits add up to 6. No longer divisible by 3, but is divisible by 5. And 7 is prime, so we're done. 3 squared times 5 times 7. Okay. Now what is the LCD? And here's what we mean by the union of factors. Let me go to red again. Just start looking at each prime factorization, and you need to have every prime factor appear in the LCD. So here I need a 2 squared, and I check to see the other denominator doesn't have any 2's in it at all, so I use 2 squared. Then I see that this denominator has a 3 in it, so I need some number of prime factors of 3, but I need at least 2 of them, because the second denominator has to be divisible by 3 squared. Then I go return to here. I see I have a 5 here. There's at least 2 factors of 2 here, of 5 here. There's only 1 here, so I only need 5 squared. If I put 5 cubed in the LCD, well, I'd have a common denominator, but I wouldn't have the least common denominator. And finally, I can see I need a 7. So this number, the least common multiple of these two numbers, 300 and 315, this number, whatever it is, if I multiplied it all out, is divisible by 300 and it's divisible by 315. Now, if I leave, since I wrote these factors down, now I can look at this least common multiple and see what additional factors I need to turn this denominator into the LCD. I've already got a 2 squared. I need 3 squared though. So I need another factor of 3. I've already got a 5 squared, but I need a 7. So now this denominator looks like the LCD, so I had to multiply top and bottom by 3 and by 7. Now what are the missing factors from this second denominator? Well, I need a 2 squared in the LCD, and I don't have that at all here. So I need 2 squared, or 4. I already have a 3 squared. I need a 5 squared. I already have a 5, so I have to multiply by 5. And I already have a 7. So this matches. 2 squared, 3 squared, 5 squared, and a 7. So I have to multiply top and bottom by 2 squared and by 5. So the new numerators are 21 21 over the LCD, whatever that is, plus 20, 4 times 5 over the LCD. And that's going to be 41 over the LCD. Now what is the LCD? Well, it's 4 times 9 times 25 times 7. And I believe I actually wrote that down. No, I didn't. So I'll leave that to the student to multiply those numbers out. But now let's see how that strategy that we just detailed here can be used to add 1/12 plus 7/20. Again, it's not so obvious what the LCD is, but if I write 12 in factored form, that's 2 squared times 3, and 20, well, what is 20? Well, I'll do it down here real quick. 2 into 10, 20 goes 10 times. It's 2 squared times 5. So what is the LCD of these two denominators? Well, I need a 2 squared, I need a 3, and I need a 5. So what's missing from this denominator for this LCD? A 5. I'll go back to blue. I need to multiply by 5, top and bottom. What's missing from this denominator? A 3. I've already got a 2 squared and a 5, so I need this 3. I multiply the denominator by 3, I got to multiply the numerator by 3. So this is 5 plus 21 is 26. And the LCD is 4 times 3 is 12. 12 times 5 is 60. And that reduces to 13/30. Okay, so that's kind of a little process that you can follow when you have to add and subtract fractions. Now let's look at the second problem. The denominators are already written in prime factored form. It's just they happen to be letters instead of numbers. So I need the LCD to look like this. I need to have at least the letter A, but I need 2 factors of A. So A squared. I need a B, but I need 2 factors of B. So there's the LCD, because when I look at this second denominator, I see I've already got an A squared and I already have at least one B. So what do I multiply top and bottom of each fraction by to turn the denominator into the LCD? I need to multiply top and bottom of this one by A. In other words, introduce an additional factor of A. And I need to introduce a B for this one. So I get 7A minus 6B all over A squared B squared. Okay. Now for this third problem, these denominators are not in factored form. A squared plus AB, whoop, not a very good B there. Well, that was horrible. This was a B. Whoops. This is a B. If I write this in factored form, there's a greatest common factor of A, so I can write it like this. Factored out an A plus 1 over, I can factor out a B. Now I have to form the LCD for those denominators. So I start remember, I'm joining the factors together. I'm forming the union of the prime factors. So the LCD has to have an A in it. It has to have an A plus B. Remember, A plus B is just like a number. It just happens to be written in the form, the sum of two terms, A and B. And then from this denominator over here, I need a B. So there's the LCD. AB times the quantity A plus B. Got to stay away from using the letter B. So what do I have to multiply top and bottom of the first fraction by to turn it into the LCD? Well, I've already got an A. I've already got an A plus B. I need a B. So I multiply top and bottom of this fraction by B. And here's the key. You have to think of that B plus 1 in the numerator as a quantity. So I will, in the end, distribute this B over the quantity B plus 1. This denominator over here is missing an A. So I'll multiply top and bottom of this fraction by A. Now I've got a common denominator. I can add the numerators. This first numerator I'll rewrite as B squared plus B. Add that on to the A. And I'll write this as AB times the quantity A plus B. Okay, now I could distribute the AB times each term inside the parentheses in the denominator. And on a multiple choice test, you might have to do that to come up with the correct answer. Okay, so we've got a little technique here for finding the least common denominator of two numbers or two expressions. Write both denominators or all denominators in factored form, and then form the union of all those factors, keeping track of the highest exponent that's required, but no higher than that. So let's go to the third page here, and talk about what a complex fraction is. I don't know why that's not going away. A complex fraction is a fraction that has more fractions in the numerator and or the denominator. So a complex fraction looks like this. Now some textbooks and teachers teach the method of combining the fractions in the numerator, combining the fractions in the denominator to get one fraction, and then multiply the numerator by the reciprocal of the denominator. And that works, but it's not the easiest method. The easiest method is to get the LCD of all the little denominators. In this case, the LCD of a 2 and a 3 is a 6. So I'm going to multiply top and bottom of the big fraction by 6. Or the LCD, I could write it like this too. Instead of the number 6, I could write it as the number 2 times 3. Top and bottom of the big fraction by the LCD. Now and the reason I'm allowed to do that is because I'm multiplying by the number 1. 6 over 6 is 1. 1 times any number is the number I started with. But when I multiply this 6 times the numerator, I have to multiply it times both terms of the numerator, and similarly for the denominator. Now when I take this 2 times 3 times the 1, when I distribute this 6 over the parentheses, I'll just get a 6. But when I take the 2 times 3 times the 1/2, the whole key is that these 2's cancel out. 2 goes into 2 once. 1 times 3 is 3. Or 1/2 of 6 is 3, however you want to think about it. In the denominator, this 6 times this 3 gives me 18. When I take 1/3 times this 2 times 3, the 3's cancel out. 3 goes into 3 once. 1 times 2 is 2. 2 times 1 is 2. So let me go back to red here. So this equals 9/20. Now you can try simplifying this using the other method. In the numerator you'd get 3/2. In the denominator you'd get 10/3. You'd multiply the numerator by the reciprocal of the denominator. Again, I think that's a more difficult method. For this problem right here, we've got 3 denominators to look at. And I want to form the LCD of all those denominators. Well, I need an A, I need a B, and this one's already got an A, B in it. So that's the LCD, AB. Multiply the numerator and the denominator of the big fraction by AB. Why do I do that? Because when I multiply this AB times both terms of the numerator, the small fractions disappear. AB times 1 over A, the A's cancel out. And I'm just left with this factor of B. B times 1 is B. When I take this AB times the 1 over B, the B's cancel out. And then A times 1 is A. When I take this AB times 1 over AB, both factors cancel out. So I'm left with 1 times 1 is 1. When I take AB times the 1, put this in parentheses for emphasis, I get AB. So I might rewrite this as A plus B, putting it in alphabetical order, over 1 plus AB. That's a lot easier than getting common denominators, adding the fractions, and then multiplying the numerator by the reciprocal of the denominator. A lot easier. Now, solving an equation containing rational expressions. These are equations because we're solving for x. And what we're going to do is multiply every term by the common denominator of all the denominators. And what will happen is that the fractions will disappear. But when you have an x in the denominator, or a variable in the denominator, you have to either check your answer, or you have to determine ahead of time what answers or solutions you will not accept. So for this first problem, I will not accept 0 as an answer. If I solve this equation and get 0 for an answer, I'll say nope, I'll cross it out. Maybe I'll get 2 answers, possibly. But for this first problem, for number 1, I mentally make note of the fact that x cannot equal 0. Because if I try to put 0 in for x, I'll get 1 over 0, which is undefined. Now, let's look at the LCD. Remember, 12 can be rewritten as 2 squared times 3, or 4 times 3. This 4 can be written as 2 squared. So what's the LCD for number 1? I need a 2 squared. I need a 3 from here. And I need an x. So there's the LCD. Now I'm going to multiply every term by that LCD. You can jot that down up here if you want. 2 squared times 3 times x, or you could just write 12x. You're going to take this 12x times every term. In other words, equals multiplied by equals are equal. Multiplication property of equality. And when I multiply this 12x times the left side of the equation, I have to multiply it times every term. So you're picturing multiplying this 12x times every term. When I take 12x times 1 over 4x, the whole key is that the x's cancel out, and 4 goes into 12 3 times. 3 times 1 is 3. When I take the 12x times the 1 over 3x, the x's cancel out. 3 goes into 12 4 times. 4 times 1 is 4, but I do have this minus sign here. X times 1 over 12, the 12's cancel out, and I get x times 1 is x. I really shouldn't put an equal sign here. Perhaps an implies sign. Normally I would be working down instead of across. But like this. So that's our solution set. Again, you could check it, but the key is it's not here. Okay. For problem number 2, same thing. X cannot be 0, so if I happen to get an answer of 0, I'm not going to accept it, I'll reject it. What's the LCD? Well, it's 5x. So I'm going to multiply 5x times every term on both sides of the equation. 5x times 3 over x, the x's cancel out, leaving 5 times 3, or 15. 5x times 2/5, the 5's cancel out. So I get the remaining factor of x times 2 is 2x. And 5x times the 1 gives me 5x. Now I have a linear equation with no fractions, no rational expressions. Subtract 2x from both sides, divide by 3. X is 5. It doesn't match our solution that we would reject. We could picture putting this 5 in here for x, the original problem. 3/5 plus 2/5 equals 5/5, which equals 1. So it also checks. Now for number 3, what's the LCD? Well, it's x minus 3. That's one factor that must appear in the LCD. And another x minus 3. That's the LCD. Okay? This is understood to have a 1 in the denominator. So I need to multiply every term by x minus 3 in order to clear the equation of fractions. So when I multiply this x minus 3 times this first term, the x minus 3's cancel out, and I just remain with x plus 1. When I take this x minus 3 times this fraction, the x minus 3's cancel out, I get a 4. Finally, when I take x minus 3 times 6, nothing cancels out, so I just get 6 times the quantity x minus 3. Oh, by the way, I forgot to mention, I don't accept an answer of 3, because if I put 3 in for x, these denominators turn to 0. So 3 is not an acceptable answer. Four plus 6x minus 18 yeah, let's do it this way. X plus 1 equals 6x minus 14. 5x equals 15. Divide by 5, x equals 3. Rejected. Solution set is the empty set. Now, if you're not used to set notation, just no solution. There's no number that you can put in here for x that will make this true. So that's why you have to do one of these two here. You either have to check your answer when you're clearing an equation of fractions where the denominator has a variable, or you have to ahead of time eliminate any solution that turns a denominator to 0. And you can identify those ahead of time, usually. So let's do one more. I need an LCD of all these denominators. Well, before I can get the LCD, I better factor that 2x plus 10 into 2 times the quantity x plus 5. So the LCD, I need a 2, I need an x plus 5, I move on to the next denominator. I've already got an x plus 5. I already have a 2. So there's your LCD. So I'm mentally picturing or jotting down on scrap paper or even up here on your test paper or your homework paper. The LCD is going to be multiplied times every term of this equation. Let me erase this down here. So when I take 2 times the quantity x plus 5 times this first fraction, both factors cancel out. So I get 1 times x plus 4 is x plus 4. Plus, when I take this LCD times the second term, the x plus 5's cancel out, and I get 2 times 5 is 10. Oh, by the way, did I forget to mention what answers I'll reject. What numbers turn these denominators to 0? Well, there's one of them. X cannot equal -5. I put a -5 in here for X, I'll get a 0. Same over here. Okay? And finally, when I take this LCD times the 3/2, the 2's cancel out, and I get 3 times the quantity, X plus 5. Now I have an equation without fractions. I'm down to X plus 14 equals 3X plus 15. (2x) equals -1. X equals -1/2. That's not in my list of rejected solutions, so this should be good. But you still might want to double check. I mean, if you want to check, you'd go -1/2 plus 4 over. If I put -1/2 in here for X, I get -1 plus 10 is 9. Plus 5 over. Put -1/2 in here, I get 4.5 or 9/2. Does that equal 3/2? Well, this is really what? 3.5, 7/2 over 9 plus, I could multiply the numerator by the reciprocal of the denominator. 5 times 2/9 is 10/9. And this is 7/18. So while I'm at it, I'll convert this to 18ths. That's 27/18, which reduces to 3/2, which matches what I had on the right side of the equation. So indeed, this does check. Okay? So that's just to give you an idea on how you can find an LCD and some of the uses for finding a least common denominator or a least common multiple. There you go.